Right, so maybe let's start. So good afternoon, everyone. Welcome to this IACS Brown Bag Lunch. And apparently it's been quite a while since we had one of those, so the rules were kind of unclear, and I had a chance to make my own. So what I decided to do is to actually speak about something that could be beneficial to everyone over here. So the topic of this talk is how to speed things up with Cython. So in the next half an hour, I would like to actually talk about this method that enables you to take parts of your existing Python code and to compile them and see to make some of use of that fast execution. So in the beginning, I'm going to just talk a little about this Python and see what are the differences. Then I'm actually going to veer a little into physics and talk about an actual project that led me into this whole Cython business. And the main part will be composed on going into this code related to this project, making some changes in order to make it faster. So let me just begin by this simple comparison between Python and C. So if you ask somebody what are the main differences, they will most likely tell you that Python is very easy to learn and program, whereas in C it's much more difficult to get going. And this has to do with the level of abstraction between these two languages, because Python is really a high-level language, meaning that you can use very simple instructions, it's very user-friendly, and a lot of the processing is actually going behind the scenes in the Python engine. However, in C, you have to take care of a lot of things on yourself. You have to take care of the memory, you have to type the types of your variables, and so on. So also in the execution, there's a difference because Python is interpreted language, meaning when you run it, something called bytecode is being generated, and this is then being run on some kind of virtual machine on top of your hardware. Whereas in C, the program actually has to be compiled first. It will show that if you have any errors in that, and after that, you get something called machine code or binary code, and this runs on that machine, on that hardware right away. So in the end, yes, Python is very easy. It's kind of slow, and C can be very difficult, but it's super fast. So now how can we combine those two approaches together? Before that, yeah, I want to actually talk a little bit about why the Python is actually slower than C. So let's take a look at this simple example of defining a variable. So in Python, if you say x equals 5, what's actually happening behind the scenes is that you create a label which is pointing to an object. And it actually carries some weight to it because first you have to have something called reference counter, because if you would do something like y equals x, another label would be created which would point to the exact same object. So the object remembers how many labels it has, and if it goes to 0, the Python garbage collector will come in and discard that. You also have to store the object type, its size, and then the actual integer is just 4 bytes. So a lot of overhead. In C, you would do this by saying integer x, so you define the type, equals 5. And now, during the compilation, the actual name and type would be actually baked into the binary code. So in the end, you would have just 4 bytes reserved in memory for that variable. So this is this example of the overhead that you're getting when you are using Python. So here comes the Cython. This is actually like a superset of Python language, or Python compiler, you could say. And it allows you to take parts of your code and pre-compile and run them in C. How much do you want to get involved with Cython depends completely on you, and the speed up you will get will depend on how much you are involved in that. And we will show that in a moment. In the basics, it looks exactly like the Python code. So if you just take the pure Python code and run it through this Cython compiler, you will get some small speed up. But what it actually does, it takes it, translates it to C, and then compiles it and run it. But all of those heavy interactions or overheads are still kept in, so we won't get anything out of that. You would still need to use some directives to instruct the compiler what it can do to make it faster, actually. And for at least it was unknown to me that this really exists, but the Cython is quite widely used in those standard libraries like NumPy or SumPy, SciPy behind the scenes. So before we get to the actual demonstration, let me talk a little bit about actual physics that inspired this venture. So today, the program that we're going to be using is going to be simulating electron water scattering process. And not to scare you off with this, I would maybe just a little history detour and tell you about the most famous scattering experiment, which was the Rutherford's scattering experiment of helium particles by gold foil. And this actually led to the discovery of an atomic nucleus. So the idea, the year is 1911, and the idea of atom is that you have electrons in this kind of a sea or pudding of positive charge, which is just there, randomly distributed. So if you would have a positively charged particle going through, nothing would really happen, right? Because the charge is just all over the place, so it doesn't matter much. However, when Rutherford actually took alpha particles and scattered them out of this gold foil, he noticed that there's actually some scattering, some different angles going on. So they thought maybe, okay, now our experiment is not that all set up, but just to be clear, let's also measure complete backscattering. Meaning, are there any particles that are actually coming back to us? And they surprisingly found a lot of them. Like, you should not see basically any, but there was a lot of them coming back, right back at them. And only explanation for that was if that positive charge was really compressed in very small volume inside of the atom. So this actually started like the physical revolution. It led to the quantum theory, because now you would have to explain why the electrons do not like collide with the nucleus, or whatever are the rules for that, right? So this was really important step in modern physics, I would say. So let's say we would like to actually simulate that process. What we would do, we would have some kind of target over here, and now we would have some projectile that would be, for instance, the alpha particle or electron in some distance v. And if you would fire it onto that target nucleus, then you would repel each other, and in the end there would be some angle theta in which the projectile would get scattered. And of course, the more you would be far away you would be from the nucleus, less the scattering you would see. If you would hit the nucleus directly, you would get that backscattering. So what physicists like to do, they actually like to express this in terms of cross sections. They express like this kind of area that actually interacts with your particle. And if you differentiate by the angle, you get something called differential cross section, which can be seen on the right. And I think these are the data for the electron and water. So you can see that depending on the energy of the projectile, you get different profiles. So slow electrons can get backscattered a lot, and they are really fast. They don't really care what's in their way, so they just pass through. This is also in logarithmic scale, so the effect is not that really big, but it's there and it's important. And why would we actually care about this at all? So the broader project here is to study what happens when highly energetic particles enter condensed phase. So for instance, electrons, if they go into water, they can of course scatter, but they actually can ionize atoms, excite them, they can attach to them. So there's actually a lot of things going on. And why would we want to understand that is because maybe of some applications like radiotherapy. So I guess also this is kind of cool concept that if you measure how much energy particles will give up as they enter some medium, you will realize that massless particles have profiles like that. So photons, X-rays, it kind of gives up energy as it goes, as it penetrates the medium. However, if you have particles like protons, electrons, ions, there's actually this phenomenon of Bragg peak, meaning that they kind of go through the medium and they deposit most of their energy at some point. So this might be maybe beneficial in radiotherapy, where you have a tumor and you know exactly where it is, so you don't want to hurt the living tissue around it. So you want to actually tune your particles in a way that you destroy just that tissue that's in some specific region. So again, this is a part of some bigger project, but let's just focus on the scattering simulations over here. And we are doing that because we want to gauge how good our model, our theoretical model is, because in the end you want to go to the experiment, to the real world, and check what are the actual measurements. And if our theoretical models match them, then okay, this is good, and we can try to infer some new information. So let's get to actual programming. I'm gonna go do the small demonstration here. So we're gonna have just two files. The first one, called water.py, will be the main routine, and I'm gonna show it to you. you don't have to pay any attention to the detail, but just to get you the overview of that. So we are just importing some modules and some parameters, and what it does, it actually generates an electron with some random V parameter, then it generates the water molecule, and then does this loop which calls the Verlet algorithm. So we are using classical electron, we are integrating Newton's equations in time, and in the end we are getting a trajectory. The electron is traveling, and we are getting like these slices in time and seeing where it goes. And in the end there's some plotting and stuff like that, but all of the heavy work is actually done through this external model, where there's the Verlet algorithm hidden, so you calculate positions, forces, velocities, and you do this over and over. And the whole machinery is hidden in the potential, because you have to define how your electron interacts with oxygen and hydrogen. So for instance, you can recognize this is the Coulombic potential, the oxygen and the electron. Maybe have some polarization going on, or maybe bring some other effects, but this is not really important over here. Let's just run the code right now and see what it does. So if I do that, it will interactively generate this plot, which will show you that we have generated an electron with some B, and this is the scattering angle that came out of it. And one by one, we have to generate those trajectories, and if you do it long enough, you can convert it to this physical differential cross-section plot on the right. And you can see it's kind of slow. I'm doing this in blocks of 10, and 10 simulations take me something like 5 seconds. So this is our reference. 5 seconds is not a good time for us. So let's try to get the Cython involved. So the first step, just to enable it, would be to actually install it onto your machine. So you just use this Python package manager, install Cython. Then you rename the file with the functions you want to actually compile. So you change the suffix from py to pix. So Python will know this is actually Cython code. And the last thing to do is actually to import this compiler module and say to it, we have Python 3. We are using just Python 3. So let's just do that. These are the only changes we have done. And if I run this, don't expect much, but it would be a little bit faster. So 4.6 seconds per 10 simulations. So this is not much, but we have done really anything. We got just the 10% speed up for free, basically, just by importing the Cython module and compiling this external file with this machinery. So that's not bad, but let's actually focus on the main feature of Cython. And that lies in actually defining the types of the variables that you use. So on the left, this is code before, and on the right, after. So for instance, we know this QO value is the charge of the oxygen. So, and this is a floating point variable, so we can just define that this is double variable, type is double, and what it tells to Cython is that it can actually throw a lot of this extra code that checks a lot of things and all of those overheads, and it can just use pure C for that variable. And you can do it for everything that you know. You can also, that the function returns double, so you put it in here, the input is also double. Maybe you have some arrays which are also double. If you have some more complicated structures like dictionaries and stuff like that, you just don't tell the compiler anything about them. You just leave them as they are, and it doesn't matter. The Cython will just take them as they are. So now, yeah, sure.
So you need to rewrite the code in the PYX file.
Yes, you need to do some small adjustment in the PYX. That's exactly right.
And so in Python, there's a typing. So when you write Python code, you can put some types there. Is that something useful?
That's also right, but there are actually other ways to make it faster. So you might be referring to one of them. But like if you have pure Python, you don't say which type it is, and you don't compile anything. So this is just how you would do it in Cython, but I'm sure there would be different ways.
But there's still a lot of work to do, as I can see.
You could say that, but for instance, if you have just one function which has to do a lot of calculations repeatedly, you call it often then I think it's worth going in and actually just saying this is double. I don't think it takes that much time. It really depends on your code, of course.
Okay.
If it's gonna be very large and the processes are all over your code, maybe that's not worth it. But if there's a single function, like in our case, where you are just constantly calling for forces at every step, then it's worth it, I guess. So if you actually do that and run the code again, you can see the 10 steps suddenly take something like 0.5 seconds. So this is much faster, and this is exactly because of the things that we have done.
That function was the only thing you changed?
No, let me show you the whole file. Of course, this is like demonstration. Even in the real world, it depends on what you do, but I've changed all of the potentials. What could have been changed and specified, I've done that. Okay. So also forces, maybe something was left out, of course. So again, it depends on your involvement. You don't have to do anything. Everything you can do just what you deem would be important.
I noticed that here you instead of using classes to encapsulate this information, you just got plain old variables. Is that a deliberate design decision?
Yeah, this is really a simplification. Usually I use arrays, but for this demonstration it would be a little bit more difficult to show you how to work with arrays. But normally you wouldn't have that simple code. This is.
The Cython, that's not because of Cython, it's just for the demo.
No, of course you can use it in the real world. Like before that, I had B in vector and F in vector, and you can work with that. But you need to get a little bit more involved in that also. So still, yeah, keep in mind this is a demo. Okay. But the speed up is real. So now we are like executing 10 times faster just because of these changes. Also, we can notice that some of functions are just defined and some of them says cdef. And this means that this function is being only called within this module. So actually, if you do that, it will actually create just a C prototype of that function, which will not be visible from the main Python function. So it can be even that much faster because you are completely getting rid of the overhead, and this is a pure C then. If you
So I'm sorry to interrupt. The cdef function is only callable from
Cython model itself.
From the module itself. You could call it from a piece of Python inside the module, but not
from the outside.
Okay.
But what you can do, you can also use cpdef. And what it does, it creates two prototypes. So one is callable from inside Cython, and one is callable from the outside. And they will have different execution speed based on from which part of the are called. But they do the same thing, of course. This doesn't change this, but it provides some additional speed up.
What is the memory overhead because of that?
Excuse me?
What is the memory overhead because of that?
Oh, I haven't really checked because this is a very small project, so I don't. Yeah, I'm not a programmer, right? I'm just a chemist guy who likes to write scripts. So I apologize if there are any pure programmers over here because I'm not going to be able to answer that. But the reason that I decided to present this is because it made my codes much faster when I use them, so when I need them. So this is just my take on this. So as I said, the most power you can get by actually just typing in the variable types and using the prototypes for C and Python separately. You need to do more work with this. And also there's this annotation tool available now, because if you run this Cython IACS, it will actually generate this HTML file. And now if you open it, it will show you your code with those colors. So white means this is already as fast as it can be, it's pure C. But if there's yellow, it hints a Python interaction going on. So for instance, over here, it says that it checks for a zero division error, because of course Python needs to check for that to throw an error, for instance. And you will notice there are still some problems with the code, and actually now you would have to go in and maybe Google those error messages and try to further improve the code to make it even faster. So this is like the routine that is primarily called, and you can still see this. There's heavy interaction with Python going on. So now, on like the next level, you actually want to go in and do some code-specific adjustments. But still, there are some nice features that everyone can use, and one of them is that you can actually now use pure C functions instead of Python ones. And what I mean by that is, if I go to the external module, instead of importing from math library, I can now use this libc math library. And instead of import, I'll say C import. So it will just, under the hood, we'll be using those pure C libraries for our function, square root, exponential, and so on. Also, I'm using these decorators, which are also in standard Python, but over here they are instructing the compiler to throw through some things out. So for instance, bounce check, if you turn it off, Python checks if, I don't know, variable, if you're calling for an array and you want a third element, if it's really there, but C doesn't care, it will just grab anything that's in the memory of that position, right? Wrap around, if you want to have like last element of array, you would use -1 in square brackets. And if you will turn it off, it will again give you some speed up. And yeah, non-check C division will actually turn off that check for dividing by 0 and stuff like that. So these are the last edits that I'm showing over here, and if I will run that, it will be a bit more faster, 0.3 seconds per 10 iterations. So this is as far as I got. Of course, there might be still some edits to be made just in like pure programming kind of style nature, because for instance, this array doesn't have to be inside some function, right? It could be outside of it, and you could make it faster just by thinking how to program things correctly, not like me. So just to go over the speedups here, pure Python 1x speed using the IACS import 1.05. The types made the heavy work, of course, and if you take some more time with that, you will do even more. If we look at our results, this enabled me to run this for much more steps, and I realized, okay, my potential is maybe not as good as I expected, because it was estimated to cross sections, but still, like the overall shape was kind of kept, but it hinted that we actually need to use something different. So in conclusion, I would say, if you have some script which is really slow for you, and you can see now how it can be sped up, use Cython. You can try that. It's great for those repetitive tasks. And of course, the Pareto rule applies. So usually 20% of changes to your code will result in 80% improvements in the end. But if you want to get serious, of course, use profiling and time your functions and so on. So this would be it right from me now, and I thank you for your attention.
With the addition of the decorators where you're turning off some checks, did that make it harder to debug errors?
Yes, that's right. Because in Python, it will throw out an error. It will say in which line it happens. But once you turn those checks off, you are going into the C territory where you got segmentation fault, right? And you don't know what's going on. So definitely, first, I guess you want to be sure that this code runs well in pure Python, and then you can go in and turn off those checks.
Try profiling it to see where the time's actually being spent now.
Yes, and I have still a large overhead in the main routine. So I guess if I would somehow wrap things more into this external file, it would be even faster. But maybe, write things in C at the beginning, and you don't have to worry about that. So I guess it kind of helps you just if you have something existing that you want to mess around with too much and you just want to maybe make it a little faster. And of course, if you would have just a pure function for like calculating Fibonacci series, you would get something like 10,000 speed up. But of course, I wanted to show a real world project where this is often not the case and you're doing a lot of things simultaneously, and you could expect something like that.
So when you use it, do you need to compile your code to scale?
It does it when you run it. So when I execute Python and the file, it will go in and it will precompile that file, and it's usually that fast that you don't see that.
So you already compile every time you run it?
Yeah, at every run. But it's kind of clever because it knows if you have edited or anything or not, and if you haven't, it will just reuse that, right? It works like if you type make and nothing changes, it will just throw the result at you. So still beneath, you are calling like GCC. You can also add some flags and stuff like that for optimizer, for instance. But at the same time, if you are using some complicated objects, Cython may not be ready to support them. So it's really better to use it just for those simple tasks for now.
Did you look at any of the alternatives to Cython? There's a whole bunch of things out there.
Yeah. I guess the PyPy or the Numba are really popular right now, but it came to me like this is the simplest thing I can do, and I found a lot of tutorials. But at the same time, the project is not that much developed right now. So maybe with those alternatives, you could go deeper and make it even faster.
So you're going to persist with this, or are you going to try something else?
I guess we kind of wrapped that part of the project. So right now I left it off, and I started to work more with pure C now. So it may be better to learn that and work purely in C.
Okay. I love C. I hate C++, but I'm using C++. But so why C?
Well, our main software that we are using right now
C.
is just in C.
I didn't know that.
But I can tell you before that I was working with something written in Fortran.
Yeah.
I can tell you C is a very large improvement over that.
Come back in a year and say that. I'd be interested.
Okay. Was there a question?
Yeah, for the example you showed, do you by chance know what the performance would be if you would run it in C? So if you would write it?
It wouldn't be that difficult to rewrite it. So if I ever go back to that project, which is possible because we are just sending it for a review, so I will tell you. All right, well, thank you so much for coming here.